Okay, so in the last class, we started looking at boiling and condensation. We have discussed that boiling and condensation is the heat transfer in which there is a change in phase takes place. Also, the rate of heat transfer is in general higher than the usual conduction and convection. The reason behind that is if you look at the typical conduction and convection, the heat transfer takes place from the bulk to from surface to the bulk, whereas in case of boiling and condensation, the heat transfer is mostly restricted in a very small region near to the surface, and therefore the heat transfer is much higher compared to the usual conduction and convection. Again, if we take a simple example of boiling water in a beaker, increase the temperature, initially the small bubbles will start forming and these will collapse even before they reach to the top. Then the evaporation from the free surface takes place if we further increase the temperature, and if you further increase the temperature beyond this, the bubbles start forming, and these bubbles will rise up vigorously through the liquid, and then these will escape from the surface. Okay, so this is a typical thing which happens in a boiling. This is the experiment which is performed in order to understand the boiling. So here there is a electrical wire which is heated. How much amount of heat is supplied, that we can easily find out by knowing the amount of voltage which is supplied. Also, the resistance of the wire is known, and therefore the surface temperature is also can be found out. So as the temperature is increased here beyond the saturation temperature, so you can see clearly when the temperature is just above the saturation temperature, maybe around less than 2 degrees Celsius. So if the excess temperature is less than equals to 2 degrees Celsius, you can clearly see the rate of vaporization of the liquid because of the bubbles is very small. So here you can see the liquid basically starts vaporizing only from the surface, and this is called as interfacial evaporation regime. But as we increase the excess temperature beyond this, from the point B onward, the small bubbles start forming, and this is nothing but the onset of nucleate boiling. Why we are calling it nucleate? Because small bubble starts forming at this location, and from B to C, which has the excess temperature between 2 and 6, the bubble starts forming, but even before these bubbles reach to the surface, these get collapsed. But beyond the point C, the stable bubbles are formed, and these vigorously go up at the surface. So from C to D, you can clearly see the stable bubble formation takes place, and these bubbles not only add turbulence in the liquid, and because of that what happens is the heat transfer coefficient increases. Heat transfer coefficient increases from C to D. So between C to D, the jets of the bubbles are formed, and this rise vigorously from the surface of the wire to uh, the outer surface. Okay. So again, point D is the point at which you get the maximum heat transfer coefficient. What happens beyond point D? From beyond point D, the bubbles which are getting formed on the surface of this wire starts collapsing directly on the surface itself, and that starts forming the film around this wire. And since a stable film is formed there, since the gas is going to have a lower heat transfer coefficient compared to the liquid, my heat transfer coefficient starts decreasing, and that is what is being seen here. So from point D onward, you can clearly see the heat transfer coefficient decreases because there is a film formation takes place, and this film also leads to the additional resistance for the heat transfer. Okay, so from point D onwards, from D to G, this particular regime is referred as film boiling. From A to B, it is referred as interfacial evaporation. From B to D, it is a nucleate boiling, and from D to G, it's a film boiling. Okay, so again, between point D and E, you can clearly see that between D and E, there is a formation of the film takes place, but this film forms and then disappears. So there is no stable film formation takes place between D and E. So film appears and then disappears. Okay, but the stable film forms from E to F. Between these points, there is a stable film formation takes place. But you can clearly see beyond these points, the rate of heat transfer still increases. You can clearly see the heat transfer coefficient HB is increasing beyond this point, because from this point onward, the radiation heat transfer starts dominating, and because of that, the rate of heat transfer increases. Again, I will just move this point because just wait. These points I will slightly move in order to give the correct information. So you can clearly see between I'll just erase this. So these values are also important. That is why I am moving this scale little bit here. So this scale should be here somewhere. Okay. So that is why I am just moving this scale little bit, so that the correct information. Okay, so the typical values, if you look at the temperature, excess temperature, I am saying, so excess temperature between A and B is between 0 to 2. Between B and D, it is between 2 to 35, and uh, above 35, there is a film boiling takes place. Okay, so now you can clearly see it is around 35. This is in a log scale, so you can clearly see this point is comes around the excess temperature T equals to 35. Okay, so that is why I have just moved this scale little bit. Okay.
Hello, sir.
Yes, please go ahead.
So can you please
Yes,
explain the point number 5 on slide number 3?
just wait. I'll just come back to that. Slide number. Okay, this point you are saying.
Sir, slide number 3.
Point number 5, isn't it? This is what you are saying.
No, sir, slide number 3, the fifth point.
This slide, are you saying?
Yes, sir.
Okay. So over the remaining section CD, a large number of vapor bubbles are generated that vigorously rise through the liquid and escape
Sir, I was saying
at the
slide
free
number
surface.
3.
Okay. Hello.
Sir, I was pointing towards slide number 3.
So this is slide you are saying.
No,
Is it
sir, this
correct?
is slide number 5. You need to go 2 slides back.
That is what I have done. There could be a little
Yes,
lag.
sir.
Now, is it okay? Now,
Yes, sir.
can you see? Is it the correct slide?
Yes, sir.
Okay, so now here the state of temperature flux data can be generated by changing the applied voltage over the reasonably wide range. So what it means is, if you look at this particular curve, how this curve is generated? This curve is generated by generating the data wide range of data, probably the heat flux versus T, isn't it? That is what we have seen here, isn't it? Heat flux versus T, correct? So the wide range of heat flux with respect to T is generated by changing the applied voltage. So what it means is, by changing the applied voltage, what you are changing is basically you are changing the T. So if you increase the voltage, what will happen is more amount of heat will be dissipated in the liquid, and because of that the surface temperature of this wire is going to increase, and what it means is the T is going to increase, the excess temperature is going to increase. Did you get it now? Hello?
Yes,
Still
sir.
not clear?
Yes, sir, it's clear. The idea is clear. But
Okay.
sir, how exactly do we go about it?
So here basically by changing the voltage, you are basically what you are doing is you are changing in a way a surface temperature. Surface temperature of this wire you are changing. Remember what is this T? T is nothing but the temperature above the boiling point,
Yes, sir.
isn't it? So in fact one of such experiment you are going to do it later on in your heat transfer lab, where you will by changing the voltage in, if I am not wrong somewhere, in your uh, but in your process control laboratory you will see that you are changing the temperature by changing the location. You can increase the voltage or decrease the voltage, and by doing that basically the temperature is increased or decreased. So this experiment you are going to do it later on in process control lab. Okay, so is
Okay.
that the question, how the temperature is going to change by changing the voltage? That is what you are trying to say.
Sir, I was asking about the governing equations. In lab, we can simply measure and find the data and then plot. But sir, I
Okay.
was thinking how voltage change can, how will translate to change in temperature.
Remember, Q is given by I square R, isn't it?
Yes, sir.
Q is given as I square R. So
Yes.
how much current you are passing through, that is going to change my amount of heat supplied, isn't
Yes.
it? And that is going to define my surface temperature.
Yes, sir. So the translation between heat and temperature flux. So, what equations do we
Yes,
use?
that
Do
is
we?
what I am said. I have said I square R is going to give me the amount of heat supplied, isn't correct? And
Yes.
the I will be dependent on how much voltage I am putting it.
Right, sir. And sir, the when we go from temperature, when we go from heat supplied to temperature, do we use convection as our
So I
method?
square R is going to be the amount of heat supplied. So that is going to be the heat flux at the wall, isn't it?
Yes,
So
sir.
heat flux at the wall will be what?
I
Heat flux
square.
at the wall is going to be H Ts minus Ts minus uh, uh,
Oh, yes, sir.
T liquid maybe, isn't it? Correct.
Yes, sir.
And again the Ts you can pinpointedly you can find out if you know the resistance of the wire. So that is also one of the experiment you are going to do. So the temperature you can measure by measuring the resistance. Okay. So both the experiments you are going to do it later on in the uh, process control. Okay. Clear?
All right. Yes, sir.
Okay. So this is what we have seen in the last class, isn't it? I will just quickly summarize. So the idea here is to, if you look at the entire boiling regime, there are three, main regimes present. One is the interfacial evaporation, then is the nucleate boiling, and then the film boiling. So if you look at the industrial operation, the most important regime in which you wanted to operate your equipments are the nucleate boiling, because here you can see you can get the highest value of the heat transfer coefficient, isn't it? You can get the highest value of the heat transfer coefficient for a minimum value of the excess temperature. You can get even a higher value of the heat transfer coefficient here in the film boiling, but you can clearly see the temperature difference here is going to be much higher, isn't it? So it's not advisable to work in a film boiling regime. So the most important boiling regime which is used in the process industry is the nucleate boiling, where you can get the highest value of the transfer coefficient. Okay. So what we have then what we have seen in the last class is uh, how the nucleation is taking place in a nucleate boiling. Correct. So we started with this Young Laplace equation. So if there is a bubble which is present in the liquid, in that case the difference in the pressure between the vapor which is present inside the bubble and the liquid, that is given by the Young Laplace equation as PV minus PL equals to 2 sigma by R, where sigma is nothing but the surface tension, It's correct.
Sir, that's why it
Now,
is not visible.
what we are
Yes.
trying to understand here is how much degree of superheat is required for the formation of a particular radius of the bubble. Why that is important? That is important because if the radius of the bubble is lower, then all such bubbles are going to get collapsed even before they reach to the surface. Okay. So we wanted to find out how much amount of superheat is required for the formation of the stable bubble. Okay. Again, here in this case, we are trying to find out the amount of superheat required for the homogeneous nucleation. Homogeneous nucleation. Of course, a lower value of superheat is required when we are looking at the formation of the bubble when there is a heterogeneous nucleation. Okay. So what is homogeneous nucleation? Homogeneous nucleation is the bubble formation takes place in the liquid itself. Okay. And whenever the bubble formation takes place on the surface of the solid, then it is called as heterogeneous nucleation. Okay. Now, in order to understand this, we started with the Clausius-Clapeyron equation. This is the standard, Clausius-Clapeyron equation, which you might have studied in your thermodynamics, isn't it? So this Clausius-Clapeyron equation is integrated for the given system where there is a bubble present in the liquid. So the pressure inside the bubble is PV, pressure inside the liquid is PL, and the temperature inside the bubble is going to be the saturation temperature Tsat, whereas the temperature inside the liquid is going to be TL. Okay, so we can integrate this particular equation between these two limits. So this is what is been done here. And after integrating, what we get is ln PV by PL is obtained as LV by R 1 by Tsat minus 1 by TL, where LV is nothing light of vaporization, the universal. Tsat is the saturation temperature and TL is nothing but the temperature of the liquid. Okay. Again, the left hand side here, which is given in a logarithmic form, ln PV by PL, this can be further, approximated. So ln PV by PL can be represented as 1 ln 1 plus PV minus PL by PL, and this bracket, if you look at ln, and this bracket can be simplified as shown on the right hand side. So here you can see ln 1 plus x can be approximated as equals to x, isn't it? So that's the approximation. So all the higher terms, x square, x cube, xn, these are omitted here. So this is the additional term which is not required here. Okay. So all the higher order terms are omitted here. Okay. So is the slides visible to everyone? Hello?
Yes, sir.
Okay. So ln PV by PL can be represented just as PV minus PL by PL. So we have used only a first term of the Taylor series expansion and all other terms are omitted here. So PV minus PL by PL equals to LV by R, and the square bracket is further simplified as TL minus Tsat divided by TL into Tsat. So again, PV minus PL we can write down from the Young Laplace equation as 2 sigma by R, so that we can put it in this equation and simplify. So by doing that, what we get is TL minus Tsat is obtained as 2 sigma R TL Tsat divided by R PL and LV, where LV is nothing but latent heat of vaporization. Okay. So again, see,
So
the
could you
temperature of the liquid will be slightly higher than the saturation temperature, 5 degree, 10 degree, isn't it? Compared to the value of TL, let's say for water, TL is for water, the TL is going to be around 115 or 105, 106, something like that, and Tsat is going to be around 100, isn't it? So the multiplication of these, if I just assume only a Tsat instead of TL, it is not going to make much difference in my values, isn't it? And therefore this equation is further approximated as Tsat square. Since TL is, remember in this case, we wanted to find out the amount of superheat required in order to form the bubble of radius R. Okay, a stable bubble of radius r. So here we can have a TL on the right hand side, but then we will have to do a trial and error to find out the degree of superheat, isn't it? So in order to avoid the trial and error, this TL into Tsat is represented as just T. Okay. So this is the equation number one. Equation number one basically enables me to find out how much amount of excess temperature is required above the saturation temperature in order to form a bubble of stable bubble of radius r. Okay, this is what we have seen in the last class. Now let us look at some sample calculations here. So suppose that okay, let me go through the detail. So up to this we have done in the last class, so that is why I have not gone through the theory in detail. So let us look at this particular slide in a little bit more detail. Okay. So this is the final expression which we have obtained. TL minus Tsat, which is nothing but the amount of superheat or amount of excess temperature required for the formation of stable bubble of radius r. So the radius of vapor bubble in mechanical equilibrium in the superheated liquid can be calculated from this particular equation. The above equation also tell us the degree of superheat necessary for the generation of tiny nucleus in the bulk liquid. So this is very important. Here we are only talking about the homogeneous nucleation. We are not talking about the heterogeneous nucleation, but such heterogeneous nucleation is shown in the figure here. When there are some cavities present in the surface, in that case these cavities can lead to the formation of the bubble even though the degree of superheat is lower than the required value. Okay, so that is what is written in the point number 3. So here you can see, however, our experience shows that a liquid boils vigorously even at a superheat of several degrees. The reason is that the bubble nuclei are formed by heterogeneous nucleation at the minute cavities present at the heating surface. So even though this equation is going to give me the amount of superheat required for the formation of the bubble, but this is going to be little bit under prediction in terms of the radius of the bubble. Okay. Okay. The bubbles are going to get formed even at a lower value of superheat because the heterogeneous nucleation is going to lead to the formation of the bubble as shown here in the figure. Is it clear to everyone? Hello? Is it all right? So this equation is valid only for the homogeneous nucleation. Just keep it, keep this in mind. This is for the homogeneous nucleation, but lower value of superheat is required for the formation of the bubble because of heterogeneous nucleation. So maybe I'll just make it red. Okay. Is it correct? Are you all able to get it? What I'm trying to say? Okay. So now let us look at some sample calculations here. So let us assume that there is a pool of water with 10 degree superheat at the atmospheric pressure. So that means the temperature is TL is at 110 degrees Celsius, whereas Tsat saturation temperature is 100 degrees Celsius. The pressure PL is 1.013 bar. The surface tension sigma is equals to 0.063 Newton per meter. The latent heat of vaporization is 4.07 into 10 raised to the power 4 kilojoule per kg per mole, and the universal gas constant is 8.314 kilojoule per Kelvin per kg mole. So we can put all these values in this particular equation and find out what will be the radius of the bubble which is going to get formed for the homogeneous nucleation. So if we put all the values here, so R comes around 3.55 into 10 raised to the power minus 6 meter. So what it means is, if I am if the bubbles are formed lower than 3.55 micrometer size, then all such bubbles are going to get collapsed in the liquid, and only the bubbles with size equals to 3.55 micrometer or above are going to remain stable in the liquid. That is what it means. Are you able to get it, what I'm trying to say here? Hello?
Yes,
Am
sir.
I audible?
Yes, sir.
So only the bubbles above the size of 3.55 micron micrometer are going to be stable in this case. Okay. Now let's look at the correlations for the nucleate boiling. Remember, I said that the nucleate boiling is the most important boiling regime as per the process applications are concerned, because the heat transfer coefficient which you are going to get it is highest in this particular regime, primarily because the bubbles, stable bubbles are formed in the boiling region, and because of these bubbles there is a vigorous turbulence is added in the liquid, and that also increases the heat transfer coefficient. Okay, so liquid boiling equipment in the process industry is designed to operate in the nucleate boiling regime, primarily because it is in this regime that the heat transfer occurs more effectively. Why we are saying effectively? Because you can have a higher value of heat transfer coefficient in a film boiling, but then the amount of superheat required for that is going to be very, very high, isn't it? So clearly the most effective heat transfer takes place only in the nucleate boiling regime. The equipment configuration is mostly of the shell and tube type. The liquid boils either in shell or tube, and the heating medium is either steam or any other hot fluid. Therefore, the correlations on boiling in or outside a horizontal or vertical tube are most important for the purpose of design. Okay, the factors which affect the nucleate boiling are density, specific heat, thermal conductivity, viscosity, surface tension, and the excess temperature. So among these boiling surface, among these again the boiling surface is also important here as a factor, but accounting the boiling surface in the heat transfer coefficients is very difficult because it changes from system to system. Okay, so there are different correlations given. One of the most widely used correlation is given by Roshenau. So the correlation given by Roshenau is as shown here. So QS, which is nothing but the heat flux, boiling heat flux in the nucleate boiling regime. So surface heat flux, this is S, denote the surface heat flux, that is given as mu L into LV into G rho L minus rho V divided by sigma raised to the power 1 by 2, and CPL by TE divided by CSF LV PRL raised to the power n, and this entire bracket raised to the power 3. Here PRL is nothing but the liquid Prandtl number. Prandtl number, PRL is the Prandtl number for liquid. Okay. Just wait. Okay. Now this equation is slightly complicated because so many parameters are required, but there is also this is slightly more accurate correlation. In this particular correlation there is a CSF and N. These are dependent on the fluid surface combination. So depending on what surface and what fluid we are using, this CSF and N will depend. So for water and stainless steel mechanically polished one, for this particular case, the CSF, this constant CSF is equals to 0.013 and N is equals to just 1. Okay, but as I said, this equation is accurate, more accurate, but a little bit more complicated because so many parameters are required. So there is one more correlation which is given by Mostinsky. So this is the correlation given by Mostinsky, which requires only 3 parameters: critical pressure, reduced pressure, and excess temperature. But this is not as accurate as this Roshenau. but you get the value of heat transfer coefficient, in the order of magnitude of this particular correlation. So order of magnitude you can get it correctly using this Mostinsky correlation. So here only three parameters are required: the critical pressure, excess temperature, and the reduced pressure. So here PR is not the Prandtl number. Keep this in mind. Here PR is a reduced pressure. Reduced pressure. Is it all right? Is it clear to everyone? Okay. So let us move to the next slide. So now again we have to find out the correlations for the critical hit. So particular slide we have looked at the correlations for the pool boiling and the nucleate boiling, heat transfer coefficient. Then the question comes in our mind, why the critical flux is also required to be estimated. The critical flux is also need to be estimated from the correlation, because while designing the transfer equipment, we wanted to make sure that the heat flux Qx or the heat transfer coefficient should lie only in the critical boiling regime. Should lie in the nuclear boiling regime. It should not cross the nuclear boiling regime and move in film boiling regime, because in film boiling regime you are going to have a lower heat transfer compared to nuclear boiling, shown here. Here you can see, if you go in a film boiling regime, here, you can see the heat transfer is lower here compared to the nuclear boiling regime. So we wanted to make sure that our equipment operates only in the nuclear boiling regime. And in order to ensure that, while designing the heat transfer equipment, we wanted to find out this critical heat transfer coefficient, critical heat, again using the correlation a priori, in order to design the equipment so that my heat transfer always remains in the nuclear boiling regime. Is it clear to all? So therefore, the correlations of the critical heat, because this these are going to enable us that, uh, uh, whether we are in the nuclear boiling regime, or that whether the heat flux obtained by the Roche. Remember here the Roshanov correlation is only going to give me QS, but whether this QS is below a critical value of Q or not, that is important, because we wanted to design the transfer equipment in order to have the critical value of the heat flux, isn't it? Okay. So the estimation of the critical heat flux is very important in the design of boiling equipment. If the temperature of the heating fluid is much higher than the boiling of the liquid, film boiling of the liquid may occur. Therefore, the critical heat flux is calculated first, and the temperature of the heating fluid may be selected accordingly so as to maintain the boiling in nucleate regime. This is very important. This is very, very important point. Critical heat flux is calculated first so as to maintain the boiling in nucleate regime. Okay. Is it clear to everyone?
Yes,
Hello?
sir. Yes, sir, it's clear.
Is it clear to everyone? Hello? One correlation given by Zubair. So again, the Qmax is nothing but the critical heat flux or the maximum heat flux corresponding to the point, corresponding to this maxima, corresponding to this point D. The heat flux is Qmax. So Qmax is given as 0.149 rho V LV sigma G rho L minus rho V divided by rho V square, and this entire bracket is to the power 1/4, where Qmax is given as watt per meter square. Here LV is nothing but the enthalpy of the vaporization of the liquid. Rho V is the rho L is the density of the liquid. G is the uh, acceleration of the gravity, and sigma is nothing but the surface tension here. Again, there is another correlation which is given by Linhard. So this is again for the Q max. So Q max is given here as Q max dash in the bracket 0.89 2.27 exponential of minus 3.44 under root r dash, where r dash is given here as, this is r dash is nothing but dimensionless radius, and this is given as r in the bracket g rho l minus rho v by sigma raised to the power 1 by 2, and this q max dash is given as 0.131 lv under root rho v in c g rho l minus rho v raised to the power 1 by 4. And you can calculate q max dash, you can calculate r dash, and then you can put it in this equation and you can calculate q max. So this equation is for the peak boiling heat flux in a horizontal cylinder.
Hello, sir.
Okay, please go ahead. Yes.
So the Zuber correlation that we have, so what container is it for? So you were not audible.
Just wait, just wait. Let me just clearly figure out. This is I am just checking whether it is for the vertical cylinder or what. That is what I'm trying to see. Just give you okay. So this Zuber correlation is so nothing is mentioned specifically here. I have to check it whether it is for the vertical cylinder or not. But I guess it is not. It is a general correlation which can be applied for all the cases. Most likely this is for the boiling in a the container. Okay, did you get it? So this is for the boiling in a container. Let me just further check whether there is some specific thing is mentioned about this correlation or not. Just wait. Okay. No, nothing is specifically mentioned. This is only for the critical heat flux when the boiling is taking place. Is it clear? Hello? Is it clear?
Yes, sir.
So this next equation is specifically for the horizontal cylinder. This is the first equation given by Zuber, is not specifically for any any specific system. My guess is this is only for the boiling in a container. So pool boiling in a container. Okay, something which we have done here.
All right, sir.
Okay. 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 So now let's look at the correlations for the film boiling. Now, as we said that our objective is primarily to restrict our boiling in a nucleate boiling regime, because we are going to get the higher heat transfer coefficient, higher value of heat transfer coefficient in the boiling regime. But in some cases, if you can't avoid working in film boiling, so the correlations given for the film boiling regime also. So this is the correlation given by Bromley, which is for the film boiling, heat transfer. So heat transfer coefficient in the film boiling is given by these particular equations, where in this particular equation, just wait, one more thing is missing here. So just a minute. Okay. Okay. So this is the equation given for the horizontal tube again. Here all these parameters here, Kv is nothing but the thermal conductivity of the vapor. Rho v is nothing but the density of the vapor. G is the acceleration due to gravity. Rho L minus rho V is the density difference between liquid and vapor. V is nothing but vapor. Is the viscosity of the vapor, and again T is nothing but the excess temperature. So this is valid for vertical tubes. Okay, so this particular equation is for the horizontal. Use it for the vertical tubes as well by replacing this 0.62 by 0.7, and D is replaced by L. Okay, so there is another equation is given. If the surface temperature is high enough to make the contribution of the radiative heat transfer important, so this is going to give me the heat transfer coefficient because of this is nothing but the convective boiling, isn't it? Correct. But in addition to that, there will be a heat transfer coefficient associated with the radiation, isn't it? So in such cases, both the heat transfer coefficients are used to calculate the actual heat transfer coefficient using this particular equation. So here H is nothing but the actual heat transfer coefficient, HB is the heat transfer coefficient corresponding to the boiling, and the HR is nothing but the heat transfer coefficient corresponding to the radiation. Remember, in the film boiling regime, even the radiation becomes important, isn't it? So the effect of radiation and the boiling both can be accounted using this particular equation to calculate the overall heat transfer coefficient H. So you just have to use HA delta T based on this particular H. Okay, is it clear to everyone? Hello? So some trial and error is required here. Here you can see in this equation H is there on the left hand side as well as in right hand side. Okay. Is it clear to everyone?
Yes, sir.
Okay. Now let us look at two problems on this. Okay. So consider a nucleate boiling of ethyl acetate at 1 atmospheric pressure. If the superheat in the liquid is 2 degrees Celsius, calculate the diameter of a cavity on the boiling surface which produces a bubble nucleus that does not collapse after release from the surface. And the second part is, if a cavity has a radius of 1 micrometer, what degree of superheat is necessary so that the bubble nucleus grows in a size after detachment from the cavity. So this is the same problem, the same problem which we have seen earlier, except that instead of water, here it is ethyl acetate, isn't it? So the equation which we will be using here is TL minus Tsat is equals to 2 sigma R Tsat square divided by R rho RPL LV. So here the degree of superheat is given, that is 5. So TL minus Tsat is given, that is equals to 5 degrees Celsius, isn't it? All other properties we can calculate for the ethyl acetate. And then ultimately what we are interested in finding is what will be the size of bubble. So R we are interested in finding. What is the value of R? So this R is going to give me the size of the bubble which is going to remain stable in the liquid. That is what we are trying to find out here. Okay, now since we are looking for the data of ethyl acetate, the temperatures are given here. The temperatures are given here, but we don't know what is the value of PL. So what is the value of pressure in the liquid, that we don't know. So this pressure in liquid can be obtained from the Antoine equations. So here the saturation temperature is 350, liquid temperature TL is 5 degrees superheat is there. So 350 plus 5, that becomes 355. So that is 82 degrees Celsius. So Antoine equations for the ethyl acetate is given by this, where log PL. So this is this is my natural log. This is log to the base 10. Okay. So natural log we represent ln. So don't confuse PL. So to the base 10. So PL for 22658 minus 1244.95 1244.95 divided by theta plus 217.88. So here theta is nothing but the temperature in degrees Celsius. So here the temperature of the liquid in degrees Celsius is 82 degrees Celsius. So that we can put it in this equation and we can back calculate the value. So comes up 1 and bar. So this equation is given where PL is represented in bar. Is it? So this equation is given in the book. This problem is a solved problem from the book. Okay. So the PL comes around 1.189 bar. Again, the correlation for the surface tension is given. So surface tension is given as 26.29 minus 0.1161 theta, where theta is nothing but temperature in degrees Celsius, and the sigma here obtained as in the unit meter. So if degrees here we get sigma 3.8 diameter become set into 10 raised to minus Newton per meter. Again, the latent heat of vaporization of the ethyl acetate is given as 3.3605 into 10 raised to the power 7. Into 10 raised to the power 7. Joule per is given in a bar, so we can use the R in a corresponding unit. So that becomes 0.08314 meter cube bar per kg mole Kelvin. Okay, so if you put all these values in this equation, TL minus Tsat we already know that is equals to 5. We have calculated sigma, so sigma we can put it here. R we know, saturation temperature we know, that is 350 degrees Celsius. PL we have calculated from these Antoine equations. LV we already know, that is 3.3605 into 10 raised to power 7 joule per kg. If we put all the values, the value of small r, which is nothing but the radius of stable bubble, that is obtained as 1.713 into 10 raised to power minus 6 meter. So 1.713 micrometer is going to be the size of the stable bubble. So if the size of my bubble is less than this particular value, then it is going to get collapse in a liquid. But all the bubbles which are having the radius above this value are going to be the stable in the liquid. Is it all right? Is it clear to everyone?
So
Yes,
can you
please go
please
ahead.
give us a background on the Antoine equation?
So Antoine equation is the correlation which gives the how the pressure varies with respect to the temperature. So this equation, all such equations you can find out from the Perry's handbook. This is also taken from the Perry's handbook. Okay, this is a standard equation given where the constants are people have found out from the experimental analysis. Okay, is it clear?
So how will we know where to pick up these equations from in
So
case
this
we
is
have?
already given. This is already given. You don't have to pick. This is already given. That is what I say. This equation is given, and also this correlation for sigma is also given.
And
Is all
so
right?
constants such as 4.22 and
This is
120.
particular case. These two correlations are given in the book. But if you wanted to do all such calculation in any industry where you wanted to particularly calculate the value, then you have to refer the standard handbooks like Perry's handbook is there. Then there are other books like properties of gases by Reed and Prosnid. So these are the books which you have to follow, where you will find out all these correlations. Is it all right?
Sir, I just wanted to ask, like the values of constants such as 1244.95, all these are fixed for
That is
ethyl
what I am
acetate.
saying. This entire thing is given for a particular system. For a ethyl acetate, these values are fixed for ethyl acetate. But if you work for some other solvent, some other forms are different, but this form is going to be the same. You get it? This form of equation is going to be the same, but this constant 4.22658 and 1244.95 and 217.88, these constants are going to be different. So Antoine equation generally given as A minus B divided by theta plus C. Some C, these are the constants which were different liquid. And these constants you can get it from the standard handbook like Perry's handbook or the properties of gases, Prosnid's Reed book by properties of gases by Reed and Prosnid's. Is it all right?
Yes, sir.
So in fact, this Antoine equation is so famous that if you type it in a only the difference is all these constants will differ for different system. Okay, can you go ahead? Hello?
Yes, sir.
Okay. Now in the second part, the question is, if the bubble size is 1 micrometer, for the bubble size of 1 micrometer, in order to have a stable bubble of 1 micrometer, what degree of superheat is required? That is what the second part of the question is. Okay. Now again, the degree of superheat required we have to calculate. That means we don't know what is the value of TL. Isn't it? Saturation temperature we already know, that is 350 Kelvin, but we don't know what is the value of TL, isn't it? And also we don't know, if we don't know the value of TL, we don't know the value of PL, isn't it? So PL we have calculated only from this Antoine equation, isn't it? So this theta is what? Theta is temperature in C. That means this is nothing but uh, this is nothing but TL minus 273, isn't it? So that is going to give me the temperature in degree Celsius, isn't it? So we can as a TL minus TL. Similarly, second correlation is given for sigma. Here also this theta is unknown because we don't know TL in the second part. So this theta can be eliminated by TL minus 273. Also this equation centimeter, isn't it? So we can convert it in a Newton per meter, isn't it? So that is what is been done. So this entire equation is converted in Newton per meter, and this theta is by TL minus 273. So now we know sigma, we know PL, we can put it in this particular equation, So that I have done. We have sigma and PL in this particular equation. So this sigma is replaced and this PL is replaced by this entire equation. So now this TL minus Tsat, TL minus Tsat is on TL 350 and right hand side is also having a unknown TL, and this in this entire equation the only unknown is TL. So we have to do a trial and error in order to calculate the value of TL. So by doing a trial and error here, the TL obtained as 350. So what it means is, in order to have a stable bubble of size 1 micrometer, one need to have a temperature of the liquid which is equals to 358. That means the degree of superheat required in this case is 8 degrees Celsius, isn't it? 350 is the saturation temperature, 358 is the TL required. So the difference is going to be 8 Kelvin or 8 degrees Celsius is the amount of superheat required for the formation of the stable bubble of 1 micrometer. Is it clear to all? Hello? Is it clear to all? Can we go ahead? Hello? Can we go ahead?
Yes.
Okay. So let us look at the another problem. Now this problem is a unsolved problem. Okay, this is not given in, this is not solved in the book. Okay. So what is been asked here is calculate the rate of boiling of water in a 0.35 meter diameter stainless steel pan at a 1 atmospheric pressure if the bottom of the pan is maintained at 115 degrees Celsius. So what is being given here is, if we assume that the saturation temperature of the water is 100 degrees Celsius, that means the degree of superheat is 15 degrees Celsius. Okay. And again the diameter of the stainless steel pan is given and the temperature, the pressure is given as 1 atmospheric pressure. So for the given condition for the water, we can find out all the properties of the water. So all the properties of the water at 109 power minus 4 second per meter square. The specific heat is 4.22 kilojoule per kg degree Celsius. Rho L is 958 kg per meter cube. That is 257 kg. Sigma, that is surface tension, is given as 0.059 Newton per meter and Prandtl number is given as 1.76. So again for the saturated steam, the density is given as 0.5955 kg per meter cube, and for stainless steel pan CSF is given as 0.013 and N is equals to just 1. So again we can use here the Roshenau correlation. So this is the Roshenau correlation we have used. So based on the Roshenau correlation, here we can put all the values here in this particular equation and calculate the QS. So QS is nothing but the heat flux at the surface. So all the values is 1.76 and rest of the power N is just 1 here, so that becomes 1.76 itself. So we have put all the values here. So by putting this, the QS comes around 462.5 kilowatt per meter square. So why this is coming in kilowatt? Because this LV you have used in kilojoule. This is 2257 I have directly multiplied. So therefore the value of QS I am going to get it in kilowatt per meter square. Is it clear to everyone? Hello?
Yes, sir.
Now, so this is what the problem is. We wanted to find out the rate of boiling of water. So this is what the heat flux we have obtained. So now in this heat flux, if we divide by latent heat of vaporization, what we are going to get is the how much amount of the water is evaporating. The rate of evaporation we are going to get it, isn't it? So that is what is being calculated here. The rate of boiling is 462.5 is nothing but the QS, the heat flux, divided by the latent heat of vaporization. So that is going to give me the rate of boiling, which is nothing but 0.205 kg per meter square second. Again, if I multiply this entire value by the area of the pan, so area of the pan is going to be pi d square by 4. So that is 0.0962. If I multiply this in the rate of boiling, I get the total rate of boiling. So 0.205 into 0.0962. So that comes around 0.011972 kg per second. And this I can convert in kg per hour also. So if you multiply this, if you multiply this 0.0111972 into 3600, you are going to get how much is the rate of vaporization per hour, isn't it? That is what you are going to get it. Correct? Is it all right? Is it clear? So this comes around, I think, 43 kg per hour is going to be the rate of vaporization, total rate of boiling. So this word you have to remember when we are saying rate of boiling. Rate of boiling is nothing but amount of water that is boiling per hour or per second. So that is what we are calculating here. So 0.01192 kg per second. Let me just do the calculation whether this is correct. This is 0.01972 and this comes around 2600. So this comes around 71 kg per hour. So is it all right? Hello? Is it all right? Are you all able to get it what we are doing?
Yes, sir.
So rate of boiling, total rate of boiling is nothing but kg per second or kg per hour. Okay. That you can directly obtain by finding the heat flux by that to give you the rate of vaporization in kg per meter square second, and then you can multiply this by area, so that will give you kg per second. You can convert kg per second into kg per hour. Now another thing which we are interested in is whether this heat flux whether is in a nucleate boiling regime or not, that we have to ensure. So how we can ensure? We can find out the heat flux again by using the Zubair correlation. Zubair correlation for the rate of maximum rate of heat flux or a critical. You can put all the values there. So 1259 kilowatt per meter square. Okay, and clearly you can see the maximum value of heat flux given by the Zubair correlation. So clearly it means that you are not crossing the nucleate boiling regime. You are not in a film boiling. So this ensures that the temperature ranges which you are using in this particular calculation are going to keep your boiling in nucleate boiling regime. Again another uh, validation here is, so the excess temperature is here 15 degrees Celsius. Remember what we said here. If you go back the figure, we have said that this D is corresponding to a T equals to 35, nearly around 35 for water, isn't it? So this D point D, which is nothing but the critical, the point of critical flux, this corresponds to the excess temperature of around 35. So that is what you are ensuring, that since in this case the excess temperature is around 50 degrees Celsius, which is much lower than this 35. So clearly the boiling in this particular problem is in a nucleate boiling regime. Is it clear to everyone? Hello? Again, there is another correlation, Mostinsky correlation. Now let us, put all the values in Mostinsky correlation. Let us find out what is the value of the heat flux obtained by using this, and what is the value of heat flux obtained by using the the Roshanov correlation, and then we can compare how much is the difference between the values obtained by these two correlations. So in Mostinsky correlation, as I said, it is a simple correlation. You required only a critical pressure, excess temperature, and a reduced pressure. So critical pressure for a given system can be given as this. Again, you can find out from the tables at the end, or you can find out this from the handbook or the property of the gases book. So this comes around, the critical pressure is 221.2 bar for the water. So critical, the reduced pressure you can obtain here as the PR minus PC, that is to give me P by to give me PR. So that is 1.013, that is the pressure of water given in the system, divided by 221.2. So the reduced pressure comes around 0.00458. So you can put in this correlation all the values are known. PR we have calculated. T is given as 50.1. Put it in this particular correlation. Coefficient is around 22 kilowatt per meter square degree Celsius, and the heat flux is given as HB into TS minus Tsat. So that is basically HB into T is given as QS. So T is 50 degrees Celsius. If you put it here, it comes around 30 kilowatt per meter square. Now, if you compare this with the values which you have obtained using Roshanov correlation, from Roshanov correlation you have obtained the value of heat flux are not same. These are, but the order of magnitude, if you look at, which is nearly the same. Okay, so these values are compared each other, that we can, we can conclude here. Hello. Can we go ahead? Is it all right? Hello.
Hello, so if we find the rate of boiling using the new QS, sir, it's giving a difference of 20 if we find it in kg. So, sir, is that okay? Which one should we consider more accurate, the Rosenhoff or the or the method given after that?
Okay, so in general, whenever such things are asked, I generally, clearly mention which correlation has to be used. And if nothing is mentioned, in that case, one has to use the Roshanov correlation, because that is more accurate compared to Mostinsky. Mostinsky's correlation is simple. Okay, if you don't want it to do the complicated calculation, and if you just wanted to get the order of magnitude for the heat flux, then you just, because here you only require the only one parameter is required. Essentially the pressure is already given, the temperature, the excess temperature is given, only the critical pressure is required. That also you can find out from the handbooks, isn't it? So the Mostinsky correlation is the easiest one, but this is going to give you the heat transfer coefficient or the heat flux in actually the order of magnitude of these values. You are going to get it from this, but the more accurate one is the Roshanov correlation. Is it clear?
Yes, sir.
Okay. So now, so far we were only looking at the boiling with no so external pressure gradient is not added in order to have the boiling. Now let us look at the forced convection boiling, in which even the external force or the external pressure gradient is applied along with the heating. Okay, so in this particular case, you can see the wall of this particular container is heated, isn't it? So initially a subcooled liquid is added to this container here. So at the bottom there is a subcooled boiling which takes place. As we move up, slowly the formation of the bubbles takes place. So this particular region is as the bubbly boiling. If you do these bubbles coalesce with each other and the slugs of the bubbles are formed and these move up. So this particular regime is referred as a slug flow. If you further move, here you can see the film of the film of the vapor starts forming at the surface here. So that this is particularly called as the annular flow. So here the film of the vapor formed on the surface here. If you further move, there is a mist flow. So there is a vapor as well as liquid, both are flowing together as in the form of mist. So there is a mist flow, and on the top of this particular layer only the vapor is present. So there is a vapor flow. So these are the different regimes present when we are looking at the forced convection boiling. So here you can see the liquid is flowing through this container by the external pressure gradient. So subcooled liquid is added here in the container and the vapor is coming out from this container and the wall of this container is heated. This wall of the container is heated. Okay, so again you can clearly up to this only up to the subcooled region there is a liquid is present predominantly. Beyond this there is a saturated nucleate boiling is taking place in the liquid, and beyond this there is a two-phase forced convection is present. So here from this point onward to this there is a two-phase flow there. So this is just the example of the forced convection boiling. Okay, when in addition to the boiling there is also a flow of the liquid is taking place because of the external applied there. Okay, is it clear to all? So we will stop here and we will start from this point onwards. So we will look at condensation phenomena in the next class. Is it all right? Hello.
Yes, sir.
So we will start with the condensation in the next class. Other than that, as I asked in the last class, so have you discussed among yourself what strategy we need to use? Is it all right to everyone?
Sir, for what matter the tutorials?
No. I am saying for among the minor and two quizzes, we will consider base 2 out of 3. We will consider for the 60 marks, and there will not be any re minor for anybody. Okay. So anyway, I am giving you one more chance. Correct? Is it all right?
Yes, sir.
Okay, then we will continue with just a slight modification in the strategy, of course, with the consultation from your side. So we will have base 2 out of 3. So minor 1, quiz 1 and quiz 2, out of these 3 examination only 2 will be considered. Base 2 will be considered and there will not be any re minor at the end. I am saying this clearly that please don't send me emails later on that please take my reminder separately. Not going to happen. So only base 2 out of these 3 will be considered and you have been given additional chance to make up the things. So it is fair in a way. Is it all right?
Yes, sir, it is.
Okay, another point which I wanted to say is I have gone through all your queries and corrected things based on whatever the queries you have put regarding the quiz 1 as well as minor. So now onward no more correction in the minor copies and the quiz copies will be entertained. Because this is what I have seen, that if somebody is not having 1 mark less because of some calculation which they have in their mind, then try to push their agenda in some way or the other by writing emails. Please go through my earlier quizzes or minor. So that is not right. Okay, So we have settled everything so far, whatever the queries or whatever the points we have raised regarding your copies. So no more changes will be entertained in your quiz marks as well as in your minor marks. I have gone through all the queries. Whoever sent me an email, I have gone through all their queries, and whenever the case was legitimate, I have also increased the marks. Okay, but no more queries will be entertained after this, particularly on quiz 1 and minor 1. Is it all right? Is it all right?
Yes, sir.
Otherwise it becomes never ending, isn't it? People keep on writing emails with the hope that some marks will get increased. uh, uh, you know uh, I'm not blaming them. It's perfectly all right from their side, but you have to understand my situation also. How many times I will go through your quiz copies again and again, isn't it? So that part generally people ignore. uh, but I don't blame you guys, isn't it? See, ultimately everybody trying to get a better grade. So I'm not blaming you. I'm not blaming anybody. I'm only asking you to, uh, please try to be considerate towards me also. That is what I'm asking. Okay. Okay, so we stop here and we will continue from this point onward in the next class.
Hello, sir.
Okay. Okay, please go ahead.
Sir, aren't we gonna do the numerical method for force convection boiling?
Numerical method for?
So this one, force convection boiling, like we did for pool boiling.
No, we are not going to look at this forced convection boiling in more detail. Only whatever we have done so far, I have given it here. But if you wanted to look at more details are given in the book. There are more correlations are also given for the forced convection boiling, isn't it? So if you wanted to get it some more detail on that, please go through the book.
All right,
Okay,
sir.
but we will not cover in the slides. But anyway, the students are free to go through the material. Okay,
Yes, sir.
is it all right?
Yes, sir.
Okay, so we stop here unless you have any more comment. Hello. So if no more comment, then I have one more point to say. I have gone through most of. Okay, maybe we will discuss this in the next class. Okay, so we stop here.
Thank you, sir.